Good afternoon and welcome to your science review with Mr. Blades. Today we're going to be discussing acceleration. Let's get started. But first, let's remind ourselves some things about velocity. Velocity, since it's a vector, is how fast you're going in a specific direction. Let's compare these velocities. Edmund goes 10 meters north at 5 meters per second. Peters goes south at 5 meters per second. And Susan goes 20 meters north at 5 meters per second. Which people have the same speed? These people all have the same speed because they are all traveling at 5 meters per second. But which people have the same velocity? Only Edmund and Susan do because they're both traveling at 5 meters per second north. So let's remind ourselves also of some small things. What's the closest you can get to your reference point, or as we sometimes say, the origin? It's 0 meters away from it. If you are 0 meters away from your origin, you are at your origin. And what does our negative position mean? Negative position means you are just away from the origin in the negative direction. But what is the slowest that you can go? 0 meters per second, likewise. But what does negative velocity mean? That means that you're headed back towards the origin. And what's the least that you can change your speed? Similarly, it's 0 meters per second per second. Again, your math teacher lied. Negative is not small. 0 is, in fact, the smallest number. But let's look again at some position versus time graphs. 0 meters, or the entire x-axis, shows our origin. The y-intercept signifies our starting point, and like you should have in your notes by now, the slope signifies the velocity, including the speed and direction. So let's take a look at some moving away position versus time graphs. Now, if our velocity is constant, we will see a straight line on a position versus time graph. And if the velocity is changing, we will see a curved line. It will be concave up if it is getting faster and concave down if it is slowing down. You can see how the curve is flattening out towards a stop on the position versus time graph in the lower right corner. For moving toward, you're going to see a negative slope on a position versus time graph. And similarly, a position versus time graph where the object is getting faster is becoming steeper and steeper, or the slope is increasing. Whereas on the one where it's getting slower, you can see again, it's flattening out towards a stop. Velocity versus time, we cannot point to a position on a velocity versus time graph. That means we can't actually know how far we are from the origin. We can only determine how far we have gone. That's our displacement, which is calculated measuring the area under the curve. Our y-intercept is our starting velocity, and the slope is our acceleration or change in velocity. Similarly, let's take a look at these graphs. A positive velocity, or constant velocity in the positive direction, is going to be a flat line, like a position graph where a flat line indicates that the position is not changing. A flat line on our constant velocity graph indicates that the velocity is not changing. A straight line on a velocity versus time graph that does have a slope above 0 indicates that the graph, or that the object, is either getting faster or slower. And the slope, the sign of the slope, tells us whether or not the acceleration is positive or negative. Now, negative velocity means moving towards the origin, and therefore would be underneath the x-axis. Again, we can see that the slope of the line indicates the rate of change of the velocity, or the acceleration. Now let's take a look at this particular graph. We start with a positive velocity. The velocity decreases with a constant slope, passes the x-intercept, and down into the negative territory. But what does this mean? The part above the x-axis, or the positive velocity, indicates that the velocity is still moving away. However, the velocity is decreasing towards 0. At the x-axis, as it crosses 0, this point tells us that the velocity is 0, or the object is stopped. And then as the velocity enters the negative region, it becomes moving towards the origin and is accelerating in the negative direction. Now let's think about something that you guys have familiarity with, your car. In this picture, there are 3 accelerators. Now let's keep in mind that in order to change the velocity, we can change the speed or the direction. So let's try to guess which 3 objects in this picture are in fact our accelerators. Well, obviously the gas pedal is an accelerator. However, the brake pedal is also an accelerator because it can slow us down. It changes our velocity. And then perhaps the trickiest, the steering wheel is an accelerator because it can change our direction. Acceleration is just the rate at which velocity changes over time. And like we've mentioned before, deceleration is not really a thing that we say. Acceleration is any change in velocity, speeding up, slowing down, or changing direction. Negative does not necessarily mean getting slower, and positive does not necessarily mean getting faster. And just like we can calculate our displacement by the area under a velocity versus time curve, we can calculate our average velocity with the area under an acceleration versus time curve. So how do we know if it's getting faster or slower? Basically, if the signs of your acceleration and velocity match, then you're getting faster. And if they're different, then you're getting slower. So if you have a positive acceleration with a positive velocity, that's getting faster. If you have a negative acceleration with a positive velocity, then you're getting slower. The acceleration due to gravity is generally considered negative. However, if you throw an object up into the air, it has a positive velocity as it travels away from the ground, but it's actually accelerating in the negative direction towards the ground. Back to this graph. Let's think of an object or a situation that would match this graph. I've already mentioned it. I'll give you a couple seconds. Since it starts off in the positive direction and slows down, stops, turns around, and accelerates towards the origin, this actually matches the velocity versus time graph of an object thrown from the ground upwards. It would slow down, stop, and then accelerate back towards the ground. Gravity is not acceleration. Gravity is a force, and when we discuss forces, you'll see what I mean, but gravity is a force that causes acceleration. And that acceleration due to gravity is negative 9.81 meters per second. And gravity acts on all things equally, big or small, moving or stationary. And just like you've probably heard, feathers and hammers would hit the floor at the exact same rate. However, only in a vacuum. A vacuum means we sucked out all the air, because if we were to drop a feather next to a hammer, then the feather would catch on the air and slowly fall. But if there's no air, then feathers and hammers would hit the ground at the exact same time. We can test this in a vacuum chamber, and Houston has one. Take a look at the picture and notice just how small the people are compared to the size of that vacuum chamber. Likewise, let's take a look at this photograph, which shows an apple and a feather falling at the same time in a vacuum. When there's no air resistance, both objects fall at the same rate, regardless of their masses or shape. I hope this discussion was helpful for you, and I'll see you in class.